Okay, so we got to get through, I want to finish up this packet, okay? All right? And basically the only thing we have left is kind of this back side. But I want to kind of show you how I want this done, because this is going to play out on how you're going to be part of the lab today. So on that back side, it says on that critical thinking question, it says draw a particle level sketch of the interior of the container on a warm summer day, then draw a particle diagram, same thing on a cold winter day, okay? So here's what you're looking for. On these particle diagrams, the idea being is that you're going to convey a couple of bits of information. One is, how are the particles existing, okay? Are they existing as a gas? Are they existing as a liquid? Are they existing as a solid, okay? And more importantly, since we're in the gas law unit, obviously, if it is a gas, like how fast is it moving? Is it moving relatively slowly? Is it moving relatively quickly, okay? So what you need to do on this one, where you've got the warm day and then you've got the cold day, okay? So you can just come in here and go, okay, I've got these little particles, right? And then you can draw the same little particles over here. So we're not changing the number of particles, okay? It's the same number of kids in the class, right? That's not what we're changing. It's the same number of kids. Fundamentally, what's the difference between the warm day and the cold day?
The warm ones are going to be moving faster?
Yeah. On a warm day, they're going to be moving faster, okay? And you all saw that when we took the balloons, in the extreme case, we dunked them in liquid nitrogen, okay? The volume of the balloons basically went to zero, okay? The particles said, we're so cold, we're not even going to move. We're not going to give any volume to this thing whatsoever. We have completely shut down. So basically, all I'm looking for is you say, okay, hey, on a warm day, these things are moving randomly pretty quickly. Okay, that's all you have to do. So on a warm day, you're going to draw bigger arrows. On a smaller day, or on a colder day, you're just going to draw them with shorter arrows. Okay, that's it. That's all you have to do. That's all I'm looking for. But what you're doing by showing the same number of particles is that you're saying, wow, I'm not changing the number of particles, but I'm changing the energy of the particles. And we can tell that by, if we took a temperature probe and we put that in there, the warm one, and again, understand the mechanism on how this deal works. If you take a temperature probe and put that in there, these particles are going to be hitting it. On a warmer day, they're going to be hitting that temperature probe with more energy. That's going to make that level on that thermometer go up. You take that and you put it in a cold day, they're not, that part, the thermometer isn't going to be hit with less energy, and it won't be as high. Okay, so understand the mechanism. So on that one, then it says, explain your drawing using at least 2 sentences. Okay, you're not writing your doctoral thesis. Okay, this is not a 5-paragraph essay. Just say, all you have to say is something like, on a warm day, the particles have more energy, and on a cold day, the particles have less energy. Just something simple like that. Okay, that's it. Now, what's important about this one is that this is going to be a sealed container. So when you deal with gas laws, basically you have 2 options. Either you can change the volume, like with the balloon, okay, we can change the volume, or the syringe, okay, or the volume is locked in place, and it's like a sealed container. So those play out differently. So like one of the things you're going to do in the lab today, you're going to blow up a balloon, okay, and you're going to take a piece of string, and you're going to measure the circumference of that balloon, okay, at room temperature. You're going to say, okay, here's the circumference of this balloon. Then we've got a freezer in the back. We're going to take those balloons, and then we're going to put them in the freezer, okay, or let them be in there for 5-10 minutes, okay, and then we're going to take them out, and we're immediately going to measure the circumference. Now, when you do this, take like a marker or something and make the mark around the balloon so that way you're measuring that same distance around. So when you took that balloon and you put it in the freezer, what do you think is going to happen to the circumference of the balloon?
Smaller.
Increase or decrease? Miles, what'd you say?
Decrease.
Why?
Because the particles are going to be moving less.
Yeah, so they're not going to be as exerting as much pressure. Now, here's the deal with balloons. So there's actually two pressures involved. So when you look at what's happening on this balloon, there's actually two pressures. You have the pressure inside, created by little particles bouncing around, but you also have pressure on the outside because we have an atmosphere, okay? So right now, everything's kind of in a state of equilibrium. So when you put it in the freezer, you're going to decrease the pressure inside the balloon, but the pressure on the outside of the balloon is going to stay the same. So it's like a tug of war. So right now, everything's like in equilibrium. So when you put this thing in that freezer, the particles on the inside go, I'm going to slow down, man. It's taking away my energy. This is bad, okay? We're still going to hit the balloon. We're just not going to have as much energy. So it's just going to kind of be a little bit chilled out. So the pressure on the outside, though, is going to relatively remain the same. So therefore, it's like this tug of war. It's like, the outside is more pressure than the inside, and that's why that's going to shrink a little bit. And that's why when we took those balloons and put that in the liquid nitrogen, that's why it went flat, because the fact those particles on the inside said, hey, kind of we're done, but we still have this atmospheric pressure, and it's going to go with that. So when you get, and again, it's something simple. So that plays out to on question number 4. It says, down below, it's like, explain why a soda balloon will contract if it is placed in the freezer. Don't make this complicated. Say, okay, it's just like what Miles said, okay? Hey, the particles on the inside aren't moving as much. There isn't as much pressure. They're more chilled out. They're not going to exert as much pressure. Hey, it's going to, that volume is going to become smaller. Now, when you get to that question number 2, okay, you got 10 particles of gas, maintains the pressure of 1.25 atmospheres. The number of gas particles reduced by half. How would the pressure change? Okay, now, this is the one where we're actually going to change the number of particles. Okay, now think this through though. Go with the second grade classroom, okay? Instead of talking about 10 gas particles, say you have 10 kids named Timmy, okay? So if you have 10 kids named Timmy, which is tough to say, 10 Timmys, and then 5 of them leave, well, what do you think is going to happen to the pressure inside the classroom? Imagine you're a teacher and half your kids leave, okay? What do you think is going to happen to your pressure?
Decrease.
It's going to become less. Why? You're going to have fewer what? Yeah, you're going to have fewer collisions. With fewer collisions, guess what? Pressure is going to drop, okay? Because of the fact that, especially if you're a teacher, it's like, half the class is gone. Oh, it's a good day, right? You know, especially if they're all little brats named Timmy. It's like, it's a good day. Anyway, there's that. So when you get done with this, hopefully on that one with that number 2, on that other side with number 13, you're going to use that P1 V1 over T1 equals P2 V2 over T2. And again, here's the deal on this one. Pay attention to the units, okay? Can you ever work in Celsius with a gas law problem? No, absolutely not. That's what some of you did on that deal yesterday, okay? It won't work. Now, that plays out to question number 6. It says, why is it incorrect to say that a sample from helium at 50 degrees is twice as hot as a sample at 25 degrees Celsius? The reason that is because of the fact that you are in Celsius, okay? Remember, Kelvin is what atoms feel. So if you're at 100 degrees Kelvin, okay, and you go to 200 degrees Kelvin, that would be doubling the temperature, okay, because that's what Kelvin is what atoms feel, okay? But if you look at this and you're at, say, 100 degrees Celsius, and you warm up to 200 degrees Celsius, well, 100 degrees Celsius is 373 Kelvin. 200 degrees would be 473 Kelvin, okay? So that's why doubling a Celsius temperature is not the same as doubling a Kelvin scale, because Kelvin is what atoms feel, okay? So that's how you want to approach that answer on number 6, is because Celsius, they say something like Celsius is not used to measure atomic level interactions. If we went from 50 Kelvin or if we went from 50 Kelvin, from 25 Kelvin to 50 Kelvin, then it would double. But it doesn't work if you're in Celsius, okay? Hopefully you get that one gets answered. All right. Are we good? Fantastic. Okay, so get that, hand it in. And stop that and then hand it back. Okay, so this is kind of like the culminating thing of all these gas laws. So some of these you're going to do, and some of these I'm going to do as like a demo. So this first one, how exciting. So literally what I'm going to do is I'm going to take a flask, okay, like such, and I'm going to take a burning piece of paper and I'm going to drop that in there, okay? And then I'm going to put not a raw egg, okay, but a hard-boiled egg without the shell in the top of the container, okay? And then we're going to see what's going to happen. So hopefully, what happens, not that I'm a surprise, but the egg falls into the flask. Now, there's an old adage in science that goes, things never suck, okay? You have an imbalance of pressure, but science never sucks, okay? So that's the deal. So keep in mind that Mother Nature is trying to equalize things. So we'll spend more time talking about this later. But basically, when things burn, what happens is that they react with oxygen in the air, and then you get carbon dioxide and water, okay? We'll spend a lot more time talking about combustion reactions. So basically what happens is that when I drop that piece of paper in there, that paper is consuming the oxygen that's in the air. So it's just like we're reducing keep this in mind, it's like we're removing the number of Timmys inside the classroom, okay? So imagine you have outside the classroom, you have inside the classroom, and you have Timmys bouncing off the walls on both sides, okay? And then on the inside of the classroom, something's happening to Timmys. The Timmys are being abducted by aliens, Timmys are going away, we don't know, Timmys are just gone. So visualize that in terms of what's going to take place. So inside this reaction, okay, you are consuming oxygen molecules. The oxygen molecules are bouncing around normally, but then we're going to take those out because they're going to be consumed as part of this reaction. Okay, so keep that in mind. So, and if y'all have done this claimed evidence reasoning CER, did they teach you that? Got a vague idea what I'm talking about? Okay, it's okay. So basically, on this claim, okay, you can say the egg goes into the flask because something simple like, oh, there's an imbalance of pressure, okay? That's it. And then on the evidence, what observation supports your claim? Well, look at the direction that the egg moved. If we had more pressure on the inside than the outside, the egg would pop out. If we have less pressure on the inside than the outside, the egg gets pushed in, okay? So what I don't want you to say is that, oh, the egg gets sucked in, okay? No, the egg doesn't get sucked in. The egg can get pushed in because of an imbalance of pressure, okay? But do not say, oh, the egg sucked, okay? No, the egg can get pushed because you have fewer particles on the inside than on the outside, and Mother Nature's trying to equalize that, okay? So, on this one, then, on that diagram, okay, include a before and after drawing. So, before, what's happening, and then after. So you want to draw particles, in an ideal world, what I'm looking for is that you're going to draw particles on both the inside and the outside, because we have atmospheric pressure. We have pressure because these billions upon billions upon billions of little oxygen and nitrogen particles are bouncing off of us, okay? Now, on the identify the following, your independent, dependent variables. Oh, man. All of those are wrong.
Hey Bert, are
Yes.
you using your lab space today?
Over there?
Yeah.
Yeah,
Yeah,
yeah.
you're getting ready to go.
Yeah. Okay. So, I cut and pasted this. So, on all these where it says identify the following, I put dependent variable twice. So, the first one, make that, I just realized this. So, where it says dependent, make the first one independent, and then the second one independent, and then the controlled variables. So, put independent, you don't have to change the dependent and the controlled variable. So basically, we're going to have 4 variables. We're going to have pressure, volume, in, and temperature. Okay? All right? This is what we're going to be dealing with. So, in this situation, we're really not going to be changing the temperature. Yeah, we're going to be throwing a piece of burning paper in there, but that paper is going to be consuming that oxygen. So my temperature is the control. We're really not changing the volume, okay, because it's a flask, it's a sealed container. So what we can control, what we're manipulating is going to be the number of particles, which is N, and then that's going to alter the pressure. So in this situation, okay, and again, here's how you want to view your independent and your dependent variable. Okay, your independent variable is the one that you can control. So in this case, our independent variable is going to be that N, which is going to be the number of particles. So the pressure is dependent upon a change in the number of particles. So our dependent variable is going to be pressure. So on that one, down below on number 1, so your independent variable, I can't believe I did that. Your independent variable is going to be your number of particles, or you can just put in, okay, it's the number of particles. Then you've got your dependent variable, which is your pressure, and then the controlled variables, okay, which is basically the ones that we're going to keep constant, that's going to be the volume and temperature, okay? Yes?
It says dependent variable twice. Is the first one independent?
Yes. Ethan, I just said that.
Sorry, I was.
Okay.
It's fine to laugh.
Well, I'm going to blame it on. I'm going to blame it on the surfer look. I think that's what affected you. Is the surfer look. Okay. But yes, yeah, we're going to make the first one.
That's not embarrassing at all.
No, we're all good. Okay. We've all been down that road. Okay. Now, on the second one, you're going to take a balloon and you're going to blow it up about yay big. Okay. We're going to blow it up about yay big. Record the temperature of the room, and let's just make, that way we don't have to do that. Let's call that 22.1 degrees Celsius. Okay? So we're just going to use that for everybody. So on that one where it says record the temperature of the room, 22.1 degrees Celsius. Okay? So that's going to be the same. Boom, we're just going to go with that number. Then, what's going to be important on this one is that you're going to draw a line around that balloon, okay? So imagine you're going to draw a line around here. Then what you're going to do is, we've got some red twine over there, and then you're going to take that twine, and you have that line drawn, and then you're going to wrap this thing around, and you're going to measure the circumference of that balloon, okay, where you have that line drawn. Some people like to put the string on first, and then they'll draw the line where the string is. Some people like to draw the line, or excuse me, and then put the string around that. I don't care which one you do, just have that way, because that way then you want to be able to go back and measure that same point. So blow it up, we'll put it back in the freezer, we'll let it sit in there. Then you're going to pull that out, measure the freezer circumference, Then on that, you're gonna draw these particles, and I tell you, at the bottom of that front page, use the length of the arrows to indicate relative velocity. So if you think they're going faster, draw bigger arrows. If you think they're going slower, draw smaller arrows, okay? Not a big deal. When you get to the part 3, getting mellow with marshmallow. So you're gonna have like the small kind of, pea-sized marshmallows. You have a syringe, and what you're gonna do is pull this out, drop the marshmallow in there, push that back together. Then what you want to do is, this is going to be important, you have to hold your finger over the end of the syringe, okay? What's this?
That's what you were doing. You're like,
That was the size of the little ones, okay? And so you're going to put you have to seal this container. So put your finger over the end of it, and then you're going to compress it, and then you're going to pull it back out. And then you're going to observe what happens to the size of the marshmallow, okay? So what I'm looking for down there on number 3, focus on imagine you're gonna have to draw a marshmallow inside that container. And basically what's happening on the compression side, what's happening to the expansion side. And ask yourself this, are you changing the number of gas particles? If you are, then I expect to see a visibly different number of gas particles on one side or the other, okay? Or is that staying the same? And if they are staying the same, then what's the difference? How do you explain the changes in the marshmallow? Okay, and that's what I'm gonna look for in that one. On number 4, you're gonna take an aluminum can, I've got them over there, and you're going to put about 2 milliliters of ethyl alcohol, okay? And notice I say about 2, okay? So, not very much. Then you take that, you're going to put it on your hot plate. Put the can itself, so imagine here's your can, okay? You're going to pour in a couple of milliliters of ethyl alcohol, put that on your hot plate. You're going to hear that thing start to boil, okay? And once it gets boiling, and you want this thing to be completely full of alcohol vapor. And you can do this with water. The reason that we use alcohol is because alcohol has a lower boiling point, okay? So in other words, what that means is that alcohol molecules aren't as sticky as water. That's why it boils at a lower temperature, okay? Water is pretty sticky. That's why it has such a relatively high temperature. So basically what's going to happen is that you're going to go from a liquid stage, you're going to give it a tremendous amount of energy, and then you're going to have this thing full of, instead of liquid alcohol, you're going to have it full of vapor alcohol, okay? And you want to let that kind of get saturated with that vapor alcohol. Then I'm going to have a tub in there, clear tub about yay big, and have some ice water in the bottom. So what you want to do is take a heat glove, okay? There should be one in the cabinet down below. You're going to have a heat glove. Grab that can, and then imagine this is your can, okay? So, imagine this is your can. You're going to grab it, boom, quickly submerge it in the water, okay? You go bing, boom, like that, okay? And hopefully you should see something very dramatic happen, all right? Hopefully. If it doesn't, we did something wrong, okay? It's pretty much a home run. You probably didn't let it heat up long enough. So, what you're going to look at is that the whole key to this is that you are going to cool this thing down rapidly. Think about what's going to happen to those particles inside that can, okay? What's going to happen to them as like a vapor? Let me give you a hint. They're going to be from going a vapor, and they're going to go back to being a liquid. What do you think occupies more space? Those alcohol molecules as a gas, or those alcohol molecules as a liquid? Which do you think occupies more space? Gas occupies a lot more space. So what happens is that when you flip that over, those particles inside are going, oh man, we're going to chill out, okay? And they're going to go back from being a gas, and they're going to cool, and then they're going to go back to being a liquid. So it's imagine this. It's 90 degrees outside, and you have all these second graders running around, okay? Bouncing around. okay? And then all of a sudden a cold front comes through and it drops the temperature from like 90 degrees down to 20. Boom, just like that. Okay, big strong cold front. Boom, drops it just like that. Imagine what's going to happen to those second graders. Oh, it's cold. Okay? And then they're going to start to huddle up because it got really, really cold and they're scared. Okay? So imagine that's what's happening inside the can. But again, keep in mind, is there pressure on the outside of the can? Yes, because we're in an atmosphere. So think that through. It's like, what's happening on the inside and then what's happening on the outside. So when you're drawing that diagram on the crushed can, okay, make sure that you are showing the fact that there are particles on the outside of that, okay? Just don't focus on what's happening on the can. You also have to focus on the fact that we have an atmosphere that's creating pressure on the outside of the can as well, okay? So when you're making those diagrams, don't just focus on what's happening inside the can. You have to focus on what's happening on the outside of the can, okay? When you get to number 5, Jack be nimble, Jack be quick, what's the following line? Did you all not learn
Jack
that?
go under the limbo stick?
Huh?
Jack go under the limbo stick?
Yes, okay? Jack be nimble, Jack be quick, Jack be more than the candlestick, okay? Very useful, yeah. So, what you're going to do with this one is that I'm going to have a little petri dish and a candle, okay? My adventure into clip art, okay? Cut and paste the little candle, okay? Not bad, all right? So what you're going to do is you're going to put some water in that petri dish. You're going to light the candle, and then you're going to take a glass jar and you're going to put that over the top of it, okay? Like this. And then you're going to observe what happens to the water level inside the jar, okay? Now again, keep this in mind when you're answering these questions. Mother Nature likes to equalize things out, okay? So if you see Mother Nature changing something, remember, Mother Nature's a lazy prima donna. Gray-haired, tie-dye wearing, Birkenstocks, chilled out, smoking a hookah pipe kind of gal, right? And so if Mother Nature is going to change something, there has to be a reason, okay? So if Mother Nature pushes that water up, it's like, man, Mother Nature's trying to chill out with something, trying to equalize something, because Mother Nature's not going to change anything unless Mother Nature has to, because she's a lazy prima donna. So when you're looking at this, keep in mind that, imagine here's the water level. Just like you, that water level is being bombarded by oxygen and nitrogen particles, okay? So the surface of that water is being pushed upon. Once you put that over there, that candle, just like what's going to happen with the egg when I burn that paper, you're going to consume oxygen molecules that are inside the container. So imagine that you have a classroom. You're reducing the number of kids inside the classroom, but you're going to still have the same number of kids on the outside. So what you're going to see is you're going to have 3 situations here where we're going to keep the same atmospheric pressure. We're going to keep the same number of kids on the outside of the container. The same with the egg, with the can, and with the candle. So in all 3 situations, we're not altering the outside pressure of the classroom. We're changing what's happening on the inside of the classroom, okay? Either by decreasing the number of kids in the classroom or decreasing the energy of the kids inside the classroom, okay? So keep that in mind. When you get to the follow-up questions, okay? So this is where we tie in a whole bunch of different things. So we're going to assume that your balloon is spherical. Realistically, it's not, but it's going to make the math work out. So you're going to know the circumference. Use the room temperature circumference, okay? Use the room temperature circumference. And knowing the circumference, you're going to find the radius. Once you know the radius, then you're going to find the volume of your balloon in cubic centimeters. Pay attention to the units. Then I've given you the density of air, 0.00123 grams per cubic centimeter. You determine the mass of the air inside the balloon, and then what we're going to do, just to make the math easy, we're going to assume that all of the gas inside the balloon is nitrogen. It's not, there's some oxygen in there, okay? But it's just gonna make it easy, because I want you to do mole conversions. So, that's why I said, assume that all the air is in nitrogen, and I admit, which it isn't, okay? But we're just going to assume that it is, and then I want you to figure out how many atoms of nitrogen are inside your balloon, okay? All right, so let's go over yonder. Actually, no, stop that. I'll go get the egg and bring that in here. That way we don't. That. Okay. So, hopefully this works. But I kind of tore the egg apart when I was getting the shell off. So basically, the egg's going to sit here like so. Okay. So I'm going to get these burning. I'm going to drop this inside of here. Okay. Okay, so hopefully those keep burning. Whoop. Okay, so a couple of things to notice. What happened to the burning splints? Anybody happen to notice what happened to the burning splints?
They burnt out
They went out. Why?
because they couldn't get any air.
But what, now, you're right. But let's talk about, there's two main components of air, nitrogen and oxygen. Nitrogen is inert, okay? Doesn't really react much, thank God, okay? So when you talk about air, the part of air that's going to react is always going to be the oxygen, okay? Because oxygen really wants to take in electrons. So basically what happened was this. Visualize this. You know that you were consuming the oxygen and it was running out because those flames, those burning splints went out. So visualize what was happening inside of it. What was happening to the number of kids inside the classroom? Increasing, decreasing, or staying the same? When those splints were burning, what was happening to the number of kids inside the classroom?
Decrease.
It's decreasing, right? So then, but what was happening to the atmospheric pressure on the outside? That stayed the same. So what happened is that you had an equilibrium shift. Okay, so this is almost like the opposite of the question about the tires. When you depress the valve on your tires, the air escapes because there's more pressure on the inside than there is on the outside. This is just the opposite. We decreased the pressure on the inside, we maintained a constant pressure on the outside, and so everybody does, oh, it sucked the A again, and scientists flip out and go, no, science never sucks, okay? Science never sucks. You have an imbalance of pressure where it got pushed in there, but it was never sucked in there because you have a difference in pressure. Okay, now the question is always, how do we get the egg out? Now what I'm going to do is not the most cool thing that I've ever done. And sometimes it works and sometimes it doesn't. So what I'm going to do, and this is where this is tough to do, and there's no way to do this and be cool, okay? So what I'm going to do is I'm going to tell you exactly what I'm going to try and do. And sometimes it works and sometimes it doesn't. What I'm going to do is I'm going to tip this thing over and I'm going to blow inside of it. Okay? So when I blow inside of it, what am I doing to the number of kids inside the classroom? Increase. So basically what I'm going to try and do is I'm going to try and reverse the process. Okay? I'm going to try and overload the pressure on the inside by blowing into it, where hopefully then it's going to try and equalize it and then push the egg back out. It works about half the time, okay? But I'm going to tell you right now, this is not going to be the coolest thing you will ever see me do, because it's just going to look goofy, okay? So don't go, where can't people look goofy? I know it does, okay? There is no way to do this and look cool, okay? So, but we're going to try it. That, and then there's like bits of like charcoal and everything else in it, because you got to get it just kind of right. Oh, come on. Trying to get some of the burnt pieces out of there. Okay. The things I do for my students. Okay. And there it goes. So, it worked. Congratulations. That's what I said. There's no way to look cool. That's typically you end up with like black charcoal in your mouth too. So how I got it out was the reverse. I overloaded the classroom. Mother Nature goes, hey, this isn't cool, and then it reversed that process, okay? So he goes, oh, you blew it out. It's like, no. Oh, it got sucked out from the outside. No, there was just a difference in pressures, okay? So what I did by blowing into it, I just reversed the process, okay? So when you see something move, it's because there was an imbalance in pressure. Got the idea? Okay, and now it's going to be out on YouTube for all the world to see me blowing on into a flask. Okay, got it? Let's go do science.